about descending tracts as well as specific lobes of the brain and their function. Now, some of this is pretty cool stuff. I think a lot of it's cool stuff, but it can get tedious trying to memorize the tracts. So with the descending pathways, we're going to see that a lot of descending pathways obviously has to do with motor function. So right away when I think descending pathways, I want you guys to think it's some type of motor pathway, and at least that kind of limits, you can cross out certain answers if you're confused. So let's talk about this picture and what it means. So we kind of already described what the pre and the post-central gyrus does. The precentral gyrus, your motor cortex. These contain your main upper motor neurons that will then come down into the spinal cord and synapse with lower motor neurons found on the anterior horn. Those lower motor neurons are the ones that then go out and goes directly into your skeletal muscles. So those are the one that releases acetylcholine, so then your muscles have an action potential and then a contraction. So in order for those muscles to contract in a voluntary, planned way, we need these motor neurons up here to stimulate them. Now, there are ways to stimulate those lower motor neurons, but when we stimulate them, it's usually part of a reflex then. In order to have actual intended voluntary movement, we need these motor neurons found on our precentral gyrus. We need them to fire, then they need to control the lower motor neurons. That's the only way we have intended movement. Now, in order to have that to happen, you need some kind of a planning. How do you want to contract that muscle? How often do you want to contract it? How strongly do you want to contract it? So then you can have a nice movement, a movement that you intended to have. Now, how many of you guys have lifted something and either found that it's way heavier than you thought or way lighter than you thought? Usually I have this problem with little kids, right? You try to pick up a little kid, they might look little, they have a jacket on, they sometimes might look pretty big, sometimes they look very small, and then you pick them up and you're almost like, oh my God, what do I do, right? I'm gonna hurt my back, I gotta put my hip into it. So it's one of those where you gotta figure out and you kind of misjudge yourself sometimes. And well, usually the reason why is because the planning part of lifting that, what you think was a small baby up, well, that planning part didn't exactly go right when you are actually lifting the baby up. So that does happen from time to time. We try to be as perfect as possible, so then we can contract the muscles as strongly as possible. So we know exactly which muscles to contract first, right? And how strongly to contract it. But it doesn't always go as planned, right? But at least there's a plan. And the planning occurs in this premotor area of your frontal lobe. Now, if you look at the postcentral gyrus, the postcentral gyrus is your somatic sensory cortex. All general sensations, pain, pressure, tickle, temperature, itch, pressure, vibration, proprioception, all will eventually end in this postcentral gyrus. Now, there are some special senses that also end here. Taste also end here. Why? Well, we're going to see that when we look at the postcentral gyrus, there's a huge area of your postcentral gyrus just for your tongue. Why? Because you want to be able to taste something that's sweet and eat more of it, so then you can store more of it. So there are reasons why we have taste buds. There are reasons why we like things that are sweet, salty, and even meaty even, right? So I know we have lots of people that want to be vegetarians and vegans. That's okay. Just keep in mind, you're eating vegetables and nobody ever has actually been on their deathbed and asked for more vegetables, right? So when you're eating this kind of stuff, usually the things that we really want are the ones that we are going to accommodate fast and the ones that we can't make in our body. You can't make salt in your body, right? You can't make whole proteins in your body. and certain amino acids we need by diet. Now, in terms of the olfactory area is found in the inferior part of the frontal lobe, and we'll talk about it later on in chapter 15. The primary auditory cortex is going to be found in your temporal lobe. And it kind of makes sense that the primary auditory cortex is found in the temporal lobe, close to the ear, also close to this area called Wernicke's, right? Where we have the ability to understand spoken language. What is weird is that the ability to understand spoken language is at a different location than the ability to understand written language, right? That's a different area altogether. The visual cortex are found in the occipital lobe, way back here, and we kind of showed that picture before about how we're able to talk, right? And I'll show it to you again coming up. Now, besides these main areas, we have association areas that processes, right, that information coming in. So here, that's in the light green, you have the somatic sensory association areas. So when you have that sensation, you can link it to previous experience. You can link it to even a person, right? So you smell something, and you need to be able to link it to memory, right? Smell somebody's cologne, perfume, and it reminds you of somebody, right? That happens from time to time. So we have a lot of association areas with our sensations here. And this is a cool picture. This is a picture of a homunculus. I don't know if I told you the story about what a homunculus is, right? So what happens in the medieval days, so after the fall, the dark age as they call it, right? Science wasn't a big thing back then. So we didn't know how, when we have sex, how that baby kind of developed in the mom, right? Was it the sperm? First of all, they don't know if it's sperm, right? Was it the fluid in males or the females that caused us to have this baby that actually formed? Being the sexist pig they were back then, it was all about the males. So they believed that in the secretion of the male, right, in that seminal fluid, that instead of little sperm cells, they have little miniature humans called homunculus, right? Miniature versions of us called homunculus, right? So the homunculus then, when you have sex, will somehow go up mom's womb and embed itself there and grow. That's what they thought, right? This is the homunculus that we use right here, right? So when you hear about homunculus, that is what it's supposed to represent here, a real small person, right? So when you take a look at this sensory homunculus, there is no uniformity, meaning that you don't have even spacing for everything. Take a look at how big your fingers, your thumb is, and your face, right? So between your hand and your face, it makes up a very small percentage of our body mass, right, and our body volume. Take a look at how much room in the sensory cortex is just for your hands and your face. Your tongue is huge right here. So are all of the somatic sensations here for your face. So between your hand and your face and your tongue, you basically have greater than 50% of your sensory cortex, just for those regions. Now, if you take a look down here, these are all of our intra-abdominal organs. That's it. This small little space for your stomach, for your kidneys, for your bladder, for the 20 feet of small intestine, for your large intestine, for your liver, for your spleen, right? So, am I getting the point across? There's a lot of room. There are a lot of organs, yet there's that little small space. That's why it's so hard to localize pain or pressure there, because there's less sensitivity there. So if you take a look at your thumb, compared to the rest of your thumb has even more sensitivity than your other fingers. Why? Well, our thumb is special, right? It allows you to grab, to hold. So that when you're holding something and grabbing something, you can have greater sensations of proprioception. So then you can, grab with more strength if you need to. So the greater the size of the body area, the greater the sensitivity. Now it's kind of weird, but look at your hands compared to your toes and your feet. Much smaller than your hands. Why? Is because we do not use our feet for anything other than wearing shoes and walking anymore. We don't grab with our feet, we don't do things with our feet, so you're not touching real things with our feet as well anymore, right? But in hands, you are. We want to also have greater sensitivity in our face as well. Now, we're going to see something very similar to this when we start talking about motor function as well. We're going to see homunculus in the precentral gyrus. Here's the homunculus of our sensory cortex. Right? Referred pain is misinterpreted pain in one region of body that is not the source of the stimulus. Organ pain usually referred to the skin. Now, you guys have heard of my story with my student that had appendicitis, right? Well, for her appendix pain started way up here. It was misinterpreted pain, as she felt it was just kind of this pain here, and then she had a hard time walking because she felt muscle pain down here. What happened? When the appendix is inflamed, but still small in size, it doesn't activate more local nerves in that area. It's not big enough. So you have diffuse pain that gets misinterpreted way up here, right? As the appendix get larger and larger, then it starts to localize in that right lower quadrant. Now, sometimes we get pancreatitis in people, and usually pancreatitis has to do with bad diet, and the most common reason in America why we have pancreatitis, alcoholism, right? People who are alcoholics get pancreatitis. Your pancreas is right here and is really deep. But most people feel pain in the shoulder blade when they have pancreatitis for some reason. It's misinterpreted pain. So we kind of know, right, if people are kind of in severe, and when you're at pancreatitis, you are in severe distress. I can look at you, you look like you are out of it. You look sick, right? And then if you complain that you just have this diffuse pain in the back, and then I'll start kind of, ordering labs to figure out what it is. In the normal lab we work are the lipase levels. People with pancreatitis, right, usually have high levels of lipase for some reason. And it starts going up and up and up until we get it treated. Now, with pancreatitis, right, it gets referred way back there, and what happens is it can turn worse, right, into chronic pancreatitis, and your pancreas you cannot live without, right? Most people die from pancreatic cancer, not because of cancer, it's because without the pancreas, you cannot digest your nutrients. And you can eat as much as you want. If you don't digest it, it comes right back out, right? And even though you eat a pretty good amount, you don't absorb the same amount. And you die because of cachexia, right? You die because you just lose so much weight, your body can't handle it. And then you pass away. Now, most of the time that we discuss cancers, right? Cancers add a few hundreds of millions of cells in our body. A lot of cells, but when we're talking about the 40 trillion cells there, what should be a few hundred million, right? No reason why it should cause us to die, but it does. And it's not because of the cancerous cells, it's what they produce and what our body produces in response, right? It causes us to just become malnourished and start to just move downwards and then die as a result of that malnutrition. All right. Now let's talk about skeletal muscles and these upper and lower motor neurons. Upper motor neurons come directly from the precentral gyrus. Well, most of them will come from the precentral gyrus. We're going to see that the upper motor neurons are also the name we give neurons up there that kind of plan, all right? They plan the movement. Think of it as this, all right? And I want you to think of our brain as the puppeteer. As a puppeteer, you need to be able to move the actual, right, puppet and the hands and the fingers and the legs and the arms in such a way that the puppet seems like they're alive and moving. But in order to do that, you need to plan on how to move your fingers. So then the strings attached to them will look like they are moving right? And the limbs attached to the strings. Looks like they're moving by themselves. But you need to plan on how to do that. That's what's happening here. We're gonna need a planning stage, and then those planning neurons are also considered upper motor neurons. So we have upper motor neurons that comes from the precentral gyrus, that comes down, and they synapse with the lower motor neurons in the ventral horn of the spinal cord. And then we'll have upper motor neurons that plan and initiate movement after you've started that planning stage. The lower motor neurons, those are the ones with the cell body in the central horn. They're the ones that leave the spinal cord by the ventral root, and they're the ones that go into the skeletal muscle directly. Right? Now, in the face, obviously, we don't have a spinal cord in the brain, right? So instead, if we want movement of the skeletal muscles of our face, which is our facial expression muscles, then the lower motor neurons are from the cranial nerves. The facial nerve will have the lower motor neurons, not the spinal cord. Right? 3 steps of voluntary movement. You need to have the initiation beginning in the premotor areas of the cerebral cortex and results in the stimulation of the upper motor neurons. So then you can have that nice, smooth type of movement that's flowing in nature. Initial planning phase of which motor neurons to activate at the proper time. Right? In other words, what happens if, right, you're taking a next step, and then instead of taking the next step in something as simple as walking, you take a next step, and instead of nice and easy, it's kind of like a violent jerk forward like this, right? It doesn't look nice and smooth. It might make you go off balance. So not only do you have to initiate it, you have to time it when you want that contraction to occur. How hard do you want that contraction to occur, right? All of that requires that initial planning phase. All we have to do is think about walking. That's a great thing, right? All we have to do is think about walking. Then the initial planning and everything kind of takes care of itself, which is good, because you don't want to have to think about how many action potentials you want triggered on your quadriceps, right? Just to walk. It takes forever to walk anywhere. So once we have that initial planning phase, we activate the upper motor neurons. The upper motor neurons have pathways, have those axons that then somehow has to descend down into the spinal cord, right? As they descend down the spinal cord, they stimulate lower motor neurons that are with cell bodies found in the anterior horn. Then they have axons that exits and causes the skeletal muscles to contract, right? The cerebral cortex interacts with the basal nuclei and the cerebellum in the planning, coordination, and then the execution of the movement in real time. So you might be taking a next step, and then kind of somebody knocks into you, and you're a little bit off balance, right? Well, now your execution of the movements have to change a little bit, because you don't have the same balance. So the cerebellum and the basal nuclei then start changing, right, that plan, so then you can make your next step without falling over. So all this, in other words, is happening in real time, which is kind of crazy. Because all we're thinking about is just movement, right? So the precentral gyrus contains 30% of your upper motor neuron. Another 30% of your upper motor neurons are found in the premotor areas. Again, upper motor neurons, very general name, right? The 30% they're talking about are the ones that allows you to plan as well. Then in the premotor area, for initial planning of the movement, the prefrontal area has nothing to do with movement. So I want you to know the difference between these two areas right here, premotor and precentral. Precentral, right, or prefrontal right here, prefrontal area has to do with motivation, foresight to plan, initiate movement, and then emotional behavior and mood. In other words, this is the personality seat right here. And here's that picture, the homunculus again. Now, this is the motor part of our homunculus. Now, if you take a look, again, look at how big your thumb is. For how small your thumb is compared to the rest of the body, this takes up a huge amount of space in your motor cortex. Again, between your fingers and your wrist, and your face and tongue. Take a look at how much room of our precentral gyrus is just in those two small regions. Now, why do we put in so much effort, so much room in our brain just for your hand and fingers and your face? Well, have you guys ever said a joke to somebody and they didn't smile, right? Or you're in an interview, right? Or you're talking with your future father-in-law and you make a joke and it goes flat, right? That kind of brings things down a little bit, right? You want people to be able to smile when you smile and everything, right? So we want, what I'm saying is facial expression is incredibly potent symbol of how we're feeling. So when somebody frowns, when somebody, is sad, you know immediately. Babies know immediately when somebody is sad. Dogs know immediately when somebody is sad from these facial expressions. So because of it, sometimes the facial expression actually belies the fact that we're lying. How many people are crying and say, no, I'm not crying, right? So how many times does that happen, right? So facial expression can actually lie about how we're actually feeling, right? Or you smile even though you're uncomfortable, right? That happens all the time, doesn't it? So, yeah, facial expression right here is very important for us to kind of mask ourselves, for us to also be true to ourselves as well, right? When we have to be. Now, if you take a look at this, take a look at how big your pharynx is, your throat. Now that includes your windpipe, right? That includes your vocal cords. Look how big your tongue is right here. Why is your tongue and your pharynx so big? Language, right? Language. So we can speak, so we can convey our thoughts to other people. You can imagine if we couldn't do that, right? It'd be really hard to describe how we feel just by pictures. So in order to have language, we need better control of our tongue, better control of our vocal cords, right? And our throat. It's kind of cool. There's a belief that language actually helped humans evolve to where we are right now. That without language, there's no way we would have gotten past the hunter-gatherer stage, right? Because we won't be able to get along with each other. Because, how do you describe how you feel, right? You can be married with somebody, and it's really hard to actually get that intimate sensation, that intimate feeling without them actually telling you sometimes, right? Because guys, we don't catch those simple things sometimes, right? So, you guys tell us over and over again. Right? That does happen. So let's take a look at these nerve tracts. And the good news about these nerve tracts is there's only a few of them. That's really the good news, right? So there's a direct pathway and an indirect pathway. The direct pathway is for maintenance of muscle tone, controlling speed and precision of skilled movements, right? This is in blue. I will kind of make sure that I don't want you to memorize it as this, right? I only want you to memorize this other part right here, right? The direct pathways right here. The direct pathways controls muscle tone, conscious fine skilled movements in the face and in the limbs, right? So you have two systems I want you to know. Cortical spinal tract, cortical bulbar tract. What's the difference? One's for the face and control the face and neck. One is for the control of limbs. The cortical spinal tract directs control for muscle tone, fine movements, skilled movements in our limbs. That's a cortical spinal tract, right? Allows us to have all this, right? Conscious, fine, skilled movements in our limbs. The cortical bulbar tract allows us to have those movements in our face, right? In our face, we don't have spinal nerves that exits. Instead, we have cranial nerves. So if we want movement so then we can chew, right? We have the corticobulbar tract coming from the cortex down into, right? So if you remember the chewing, that's trigeminal. Where's the trigeminal? In the pons. So the pons looks like a bulb. That's why they call it bulbar. I know, sounds stupid, right? But it kind of looks like a bulb, the brainstem area. So the corticobulbar comes from the cortex to the bulbular area of your brainstem. So when we chew, the trigeminal nerve gets activated, so then we can chew. When we talk and say words, right, we need to control our tongue, so we need the hypoglossal nerve to be activated as well. So all the movements we want in the face will somehow be directed by your cranial nerves for that movement. We want to smile. The corticobulbar tract activates branches of the facial nerve, so then you can smile, right? I know, right? It's just kind of a weird thing to describe it that way. Right. Again, review this for the corticobulbar. The lower motor neurons of the corticobulbar tracts are branches of the cranial nerves. The cranial nerves then will be kind of different depending on the movement we want. If you want to frown, right, then you'll have the facial nerve providing the lower motor neuron. That kind of stuff. Right. The last one, indirect pathway, controls conscious and subconscious movements in the trunk and proximal limbs. This is the one I want you to memorize, is a vestibular spinal tract. Vestibular means balance, right, and equilibrium. So vestibular spinal comes from this vestibular region to the spinal cord. What does it allow us to do? Helps maintain an upright posture so we don't fall over. Again, there's a lot of area in our brain and of our body. The sole purpose is just to prevent falling. Do you guys know why it's so important to prevent falling? All right, you guys know the statistics for what happens if older people over the age of 75 fall and break a leg, right? The morbidity, mortality rate is astronomical. 50% of those people that break a leg die within the first year, right? 50%. Only 15% ever recover to regain their normal activity. That's it, only 15%, right? Now, the crazy thing is, as you get older, the numbers become actually better, right? If you're 85, you're not moving around much anyway, so, right, regaining your normal activity isn't much. So that actually becomes like 25%. But yeah, you know, if you have older parents, and you know you're gonna have older grandparents, so if you really love them, you gotta make sure that you can convince them into using a walker or a cane, right? I know my parents have a hard time, right? Even with me, so I know you gotta have an uphill challenge too, right? So yeah, these pathways are there, they're redundant, they allow us hopefully to stay upright. All right, basal nuclei, important in planning, organizing, coordinating movements and posture. So with the basal nuclei right here, all right, so these allows us to have fine tuning of motor neurons, activity to cause our nice smooth motion.